In this lecture, we're going to look at exponential functions. So we're going to recognize the shape of exponential functions. We're going to distinguish between a growth and a decay function. We're going to define the exponential e and recall its approximate numerical value. We want to recognize when an equation is an exponential model, and we want to determine the physical meanings of constants and parameters within our exponential function. So an exponential model takes the form of y equals b times e to the mx. Given an exponential system in the form of y equals b e to the mx plus c. When m is 0, y is equal to b plus c regardless of the value of x, so you get a constant. When m is greater than 0, the model is a growth function. When m is less than 0, we have a decay function. Some examples of exponential relationships are you have the voltage across a capacitor, the rate of the spread of an infection such as smallpox, and the growth of bacteria. All the exponents must be dimensionless and thus unitless, so this combination of time divided by RC, or C times T, or G times T must turn out to be unitless. So what is E? E is the exponential constant. It's a transcendental number. It's an irrational number. It's the base of the natural logarithm function. So the natural log of e to the x is x, and e to the natural log of x is x. The rounded value is 2.7121828. It's Euler's number. It's Napier's constant. So what are the units of the constant 2? So we have I is equal to 2 e to the 0.72 v. It is a growth function, and they are milliamps because we need current, and anything in our exponent is dimensionless, so our e term is dimensionless. Therefore, our 2 must have units of milliamps. So what are the units of the constant 0.72? Well, again, we need this exponent to be dimensionless, so it's something times volts, so our something must have units of 1 over volts. If we compare our two equations together, since E is unitless, I and B must have the same volts, and the exponent must be unitless, so M times V has to be unitless. So in another example, we have I is equal to 250 v divided by t. So what are the constants of what are the units of the constant 205? Again, there's still, if m is 1 over volts, m is equal to 205 over t. So 205 over t has to equal 1 over volts. 205 is Kelvin per volt. So what is the temperature the circuit is operating at? So we have 205 over T is equal to 0.72. So T is equal to 205 kelvins per volt divided by 0.72 per volt, which is 285 Kelvin, or 54 degrees Fahrenheit. If I have another example of T is equal to T naught e to the minus KT, I'm looking at the temperature decay since my M is negative. What are the units of 300? Well, the units of 300 must be degrees Fahrenheit because, again, the entire exponential term is unitless. So what is the physical meaning of the constant 300? It is the initial temperature. What are the units of the exponent minus 0.014? So again, the entire exponent must be unitless, and so it's something times time, which is in the units of minutes, so it has to be 1 over minutes. So if we compare the theoretical equation to our trendline equation, E is unitless, so T and T naught must have the same units. The exponent must be unitless, so KT must be unitless. So let's look at some graph shapes. We have L is equal to B times F to the 0.5. If I plot F on the x-axis and L on the y-axis, I have a power relationship between L and F, and it is square root type. It is a fractional power, and a fractional power graph appears as graph G. So if I plot L on the x-axis and B on the y-axis, my relationship between L and B is linear, so I'm going to get a linear graph, which is graph A. If I plot F on the x-axis and B on the y-axis, my relationship between B and F is a power function, and it is a squared power function, so it is a negative 2 in that case, so we're going to get graph D. So we want to determine the type of expression, linear, power, or exponential, then based on that choose the values and parameters for M and B. So if I have volumetric flow rate is equal to 406 plus 85T, I have a linear relationship. M is equal to 85 liters per minute degree Celsius, and B is 406 liters per minute. If I have L is equal to 98 times, if I have my yards, my length is equal to 98 times my power cubed, it's a power relationship. M is equal to 3 and it is unitless. B is equal to 98 yards per horsepower cubed. If I have a graph of temperature is equal to 150 times e to the minus 0.5 t, I have an exponential function. M is minus 0.5 and it has units of 1 over days, and B is 150 Kelvin. If I have F is equal to 45 mu, it is a linear relationship. M is 45 and B is 0. So those are some examples of exponential functions and how to evaluate the M and B for exponential functions and their graph shapes. Also, we need to be able to determine if we have a power relationship, an exponential relationship, or a linear relationship, and be able to expect what those graphs are going to look like. Next week, we are going to look at actually employing trend lines in models.